that's what we're going to be talking about. Air, oh shucks, we're not going to talk about it. You and I are going to do a lot of demonstrations or maybe even experiments, depending on what it is. And we're going to be using, for many of these, a vacuum chamber. This is called a chamber. In the old days, it used to be called a bell jar because it looked like a bell. No more. Made of plastic. You can see the bottom of it is open. I can stick my hand way in there. Easily fits on a base plate. I can pick it up and down without any problem at all. I'll turn on my vacuum pump, open a valve, and I'm starting to remove air out of this, and look at what's happening. It's stuck together. And it's stuck together so hard, I can't pull it apart. You can't pull it apart. Two of you can't pull it apart. Three of you can't pull it apart. You're all a bunch of weaknesses. No, that's not the case. It's the fact that there's a lot of force pushing down and pushing up. Atmospheric pressure. So that's the first thing that we have to work on. In order to get anything inside of this right now, we have to do the following. You can hear the air, the atmosphere going in through the hose into here. Easy as pie, it comes apart. So, we're ready to start our work right now. I need a volunteer to help me with this, because this is going to be a... Sir, would you like to come up? You can see what it is. It's called an earth bar. Because if you're studying astronomy, there's a heck of a lot of different planets out there, right? And we're not concerned with Mars or Pluto. Well, maybe Pluto's not a planet anymore, but we're not concerned because we're right here on Earth. So we're going to work with this. This bar says, if I can pull your hand off just a moment, right here, it says 1 atmosphere. So that's our starting point. All right, if you want to hang on to it. We're going to work with this. The bar itself is 1 inch by 1 inch, 1 inch, 1 inch. And you'll find, you already have found it, when you're involved in science, you're also involved in math. The two kind of go hand in hand. So we're going to do a pop math quiz right now. Is that okay? It's all right? 1 times 1 is
1.
Inch times inch is
Inch squared.
inch squared. So the cross section of this bar, taking all the answers that everybody's given, is 1 square inch. The bar is simulating 1 atmosphere. It's a simulation. That's not really 1 atmosphere. Because atmosphere, the pressure goes from the bottom of the bar way down here all the way up. Doesn't stop here. It keeps going. Ends up at about 93 kilometers. Are you using metric units of measurement? No? Yes?
I prefer the normal.
You're going to use the English units? Okay. 51 something miles up. Can you throw a baseball that far?
Yes.
Absolutely.
A long ways up there. There's no way that you're going to be able to reproduce that easily because that gets to the point of inner space. That's how far the air that you breathe way back there. Yeah. That's how far up there is still part of that gas. Most of the gas is down at the bottom of the bar. Very little of it up there. So we're just like fish swimming in a fishbowl down here with all of the pressure. Golly, it says how much pressure right there, right? Which is
14.7
pounds. 14.7 Actually, 14.7 pounds per square inch. And you know how big a square inch is because the bar is that. Have you felt that pressure on you? 14.7 pounds per square inch? God, I'll measure the number. You've got 11 million square inches on you. Multiplied by 14.7. How come you're not lying flat on the floor under all that load? Were you born in it? Do you work in it? Do you go to school in it? Sure, we're used to it now. And we've got pressure inside of this exerting outward. So we can make do with it. Here is the problem. We're down in the bottom of this ocean of air, atmosphere, but when we get up near the top, or we're working inside of a simulated chamber, and let's pick one not this size, but let's pick one about the size of the room, which is at the NASA facility in Houston, and we simulate the pressure up at the top of our inner space, you're going to last about that long because there's not much gas there, not much air, not much oxygen. So we're concerned down here, but we have to know what's happening in low pressure or a vacuum up there. Great. I thank you for all that help. A round of applause. We've got a definition of our pressure now, and we're ready to start using it. I might need somebody to help me with a Coca-Cola. Who wants to help on Coca-Cola? This young lady here put her hand. You didn't get it all the way up.
Yeah.
But I would like you to help with this. So if you would come up right here for the Coca-Cola can. As you see, I couldn't resist, so I already drank all of the cola. Can's open now. So when I do this, there's no Coca-Cola coming out, right? What's coming out?
Air.
Air, because it's a surrounding container. Throw it on the counter, and it's still got air inside, and the air might go out, but it's going to come right back in again. So here's what we're going to do. We're going to hold this together like that. Why don't you hang on to it so I don't knock it off the table? I'm kind of clumsy. All right, we've got a hose, so if you walk a little closer here, we're going to attach this like so.
Is it going to explode?
Well, that's a good question. Anybody have a hypothesis of what this is going to do? Yes, young lady.
It's going to implode.
Implode.
Not explode, but it's going to
Nice science word.
Great word.
Oh, I thought you were going to blow air into it.
All right, hold on. By the way, have you ever seen an illustration of the Statue of Liberty in the New York Harbor? A picture of it?
Have you ever seen such a...
See the picture? Holds a book in one hand, and what's the other hand doing? Holding a torch. Up high. Ah, here's Miss Statue of Liberty right here. Hold that torch up high. Because what we're going to do now is remove a little bit of the air out of it as soon as we put on safety glasses. So I'll hang this. I'm holding this out of the way so you can put on the glasses because there's a lot of pressure in here. Not external pressure, internal. All right? And I'd like you to hold it right about there. Great. I'm going to stick on glasses because I'm right next to all of this. And on the count of 3, after I get the pump started, we're going to take a little bit of air out. Oh, up high. Really up there. Okay. 1, 2, 3. Wow. That didn't take much pressure, did it?
That was very impressive.
It imploded very nicely. The whole can now is kind of mushed into this shape. by what?
Air.
What air?
The air that came out of it. Air on the outside.
What?
Stuck. I don't know.
We removed gas from the inside, so we did indeed have a vacuum in there. But what did that have to do with mushing the can?
There's no air in there and it just all come in.
Why?
Pressure? No, it's
Because pressure didn't hold it.
What's surrounding the can? Atmospheric pressure. That's what did it. The atmosphere outside, vacuum inside, there's a pressure differential, can got mushed. Tell you what, you now have a great example to take home with you and show what you did in school today. So if you'd like to take that demo, round of applause. Level can, big 55-gallon drum, doesn't make any difference. You start removing the air from the inside and you create a pressure differential. The container is going to mush unless it's very, very strong. Can's made out of aluminum, very thin. That doesn't do that much. All right, let's get some of this over there ready. And we're ready to talk about Magdeburg hemispheres. What is a Magdeburg hemisphere? Anybody probably haven't come across it in your textbooks because it's kind of an obscure experiment that was done. So let's back up a minute. What in the heck is a hemisphere?
Hemispheres are on globe.
Okay, you have hemispheres with a globe, but what is a hemisphere? Not the globe, not the world, but what's a sphere?
Is it like a circle?
No,
Sphere?
not a circle.
This is a sphere.
Yeah, it's a sphere, but it's not a circle. It has to be a ball, a globe, an orb, something like that. And a hemisphere is half of that, so here's a couple of hemispheres. Now, when you get to the world, you can say, yeah, there's a northern hemisphere and a southern hemisphere, meaning that you split the world in half. All right, but we're not going to do that. But we're now ready for this gentleman right here to come up and assist us with this experiment. Because we're going to do something special now. Let me get this hose off. Unlike the soda pop can, these are made of cast iron. Heavy, strong. So I want you to hold it with 2 hands. Hold it right up there. And we're going to set this on top. Like that. And tell you what, I'm going to get out of the way so that you can show everybody. Turn slightly, right like that. You're going to be able to show everybody what's happening. Better hold them with 2 hands because they're heavy. Get them situated, right like that. Got to hold them. Okay. Going to turn on the pump. Going to do a little bit of quick evacuation. Tell you what, we should look inside of these before we go too far. So, you show everyone the inside of the 2 hemispheres, or the sphere. No, don't play with it. Just pull them apart.
I can't.
Oh, come on now. You're not a 97-pound weakling. I'll give you some help. On the count of 3, I'll grunt for you, and you pull them apart. Ready? 1, 2. Okay, hang on to it. Oh, boy, they are tightly together. How are we going to get them apart?
gotta release
Let the air back in.
Oh boy. All right, hold on to that handle. See this blue valve? Change it from that attitude to that attitude. That's all it took. Why couldn't we separate the two hemispheres? Anybody? You have an answer? Anybody have an answer?
There's
Why
no
couldn't-
air in there. And you just let a bunch of air in. It can...
Okay. I agree with your first statement. There is not much air. I modified it a little bit inside. Why couldn't we pull them apart? Because there was not much air in there.
The pressure.
Which pressure?
From the outside coming in the atmosphere.
Atmosphere.
Ching.
It all gets down to the fact there's a pressure differential. We remove the gas from the inside, and when you put that together, and you've got gas on the outside, 286 pounds by calculation it takes to separate these. A lot of pressure. Wow. Boy, thank you, Connie, for doing that. A round of applause.
Yeah, Mark. Good job.
Some of you that play a musical instrument undoubtedly know what this device is. Don't you? Anybody play a musical instrument? No? Pardon me?
Is it for me
Tuning fork. Yeah. If you've got piano, you've got a guitar. Any of you play a guitar? Piano? Piano. Strings stretch, don't they? Yeah, for a period of time. So you use the device like this, and you can see there's lines on it. And that's so you can adjust these. Middle C, right there. Oh boy. And then we can move the weights down and get to something in the order of middle G. And we've got a way of tuning the piano, tuning fork. Okay? We're going to work not with the tuning fork, we're going to work with another device as soon as our volunteer gets up here to get all of this put together. I have to keep pulling this hose on and off because I don't have a big enough valve to manipulate it back and forth. There we go. And our expert right here is going to come up and work with this. This is not a magic box. It's just a producer. So, in the yellow box, hold it up high so everybody can see, is a sound emanator. Make sound out of that. The round black knob. Directly above it is a red lamp, an LED. And inside is a battery and wires. So when we put that all together, and you flip the switch right there, do it, we get a pleasing sound coming out of it. And you can notice the red light is lit, correct? Hold it up high so everybody can see. All right. Okay, you can shut off. So we know that it produces sound and shows light. And if we set that right about there, facing out with the sound producer, yep, we're ready to do something called quick as a bunny. Bunny rabbits are pretty fast, aren't they?
Yeah.
We're going to do something fast. You're going to flip the switch when I tell you to, and I'm going to immediately drop this down on the seal.
Okay.
And you better pull your hands out fast. All right, we're ready to go. Flip the switch. Now, even though we barricaded it, you can still hear it because you're right next to it, like me. But the folks in the back, they can't hear it.
Young ears.
Must be. Oh, I can hear it now. Yeah, when you get old, the eardrum gets a little leathery. Actually, I've been to too many Grateful Dead concerts over in the city, and all of that makes the ears get a little stiff. All right, we're ready to proceed. I wonder at times off of the subject, talking about other things. Got a set of glasses for you, and a set for me, because we're now going to do something. In fact, I'm going to step in back of you and have you by the pump so that you can be the pump operator. Well, you'll get a star for that. Now, whether that counts as a point, I can't tell you. Turn on the pump right there. All right. We're now ready to remove air from the chamber, and you do that by pushing the red valve up. The handle on it goes straight up. And now we're starting to remove air. Those of you that can see the scale on the gauge, the needle is moving to a better and better and better vacuum. And we're in grass growing time, twiddling the thumbs, just waiting to remove most of the air from this chamber. But not all of the air, right? Pump's not good enough to do that. But, it's probably far enough along now. Push the red lever down. Turn off the pump. Oh, shucks. You didn't tell me to check the battery. I forgot to do that. So the sound, we can't hear it anymore. The battery's dead, there's no sound.
The LED light is on.
No way.
No way.
Okay. How come the LED is on?
Because the battery's on.
I think
There's no air to the noise.
Sorry, you're going to have to speak a little louder for my tired old ears.
There's no air, so there's no noise.
There's
no
no
air,
air,
not
so there's
air.
no noise.
I heard what he said the second time. And there is no air. Why isn't there any noise?
No way for the sound to travel.
Come on, keep going. What does the atmosphere got to do with the sound?
It's all around it. I don't know. It's brown and stuff out there.
Sound waves.
It's
Sound
blocking
waves.
sound
Okay,
waves.
we're almost at the point. What do the sound waves have to do with the sound that's being produced in here coming out here?
There's
Travel
no way for
through
the
air.
sound waves to go because the atmosphere all around it.
That's what it gets to. There's not enough gas density in this chamber for the sound that's being produced right now to travel the short distance to the wall here where it comes out. And what was said before about the movies and television that shows something blowing up in space and a big boom is all horse bucket. Because there is no way to transmit sound in space for the human ear. Yes, sir.
If you're in like a spaceship, can you hear stuff? Or is it super?
Oh, sure. If you're in a spaceship, you're in an environment of gas close to atmospheric pressure. Yeah, sure. Somebody opens a potato chip bag, you're going to hear it. If somebody rolls a marble across the concrete floor, you're going to hear it. Outside, Alrighty. Let's prove that what they said is correct. Come over here to this valve that's sticking straight up and turn it so it's horizontal. Sound back again? Yeah. Is that unknown? No. We all have a supposition that that's what's going to happen. So we know that in space, there's not going to be any sound transmission that we can hear. There is a different way of transmitting sound from a spaceship to Earth.
Radio
Sure,
wave.
not by sound waves. It's an electromagnetic force. All righty. I appreciate that help. Round of applause. We're just about at waiting time now, so we can get to the next room. There's more that we could show and talk talk about and do in the way of program. We can show that you can boil water in vacuum.
Yeah.
And if you do it long enough, you can turn the liquid water into solid water. But there's not enough time.
What's solid water?
Ice?
Pardon me?
Oh, nice.
Oh, yeah.
That was so pretty.
You turn the water directly through the vapor phase into the solid phase, called the triple point. It works nice.
Can you boil the water for me? Do that?
Do we have enough time?
Yeah.
Okay.
Boil that water.
Boil that water.
Somebody come up and prove that we're not starting out with hot water. Come on. We'll do this quickly.
Okay, what does water normally boil at? What temperature?
212 degrees Fahrenheit.
Where on the planet will it boil at 212 degrees Fahrenheit? Top of the mountain or at sea level?
Sea level.
Are we at sea level here? Yeah.
No.
13 feet above. Okay.
Okay.
Everybody agree that we're at 13 feet above sea level?
Yes.
Everybody agree the water boils at 212?
Yes.
Okay, now let's watch.
Alrighty, we got an expert here, and I'll adjust this to Fahrenheit. There you are, Fahrenheit. Hang on to the thermometer at the top. Stick it in the water so we can see what the water temperature is. That way you know that if we're not starting out with hot water. What do we, just the first two numbers jump off of the decimal. 71 degrees. Okay. Now I would like you to put 5 milliliters, there's the 5 line right there, put 5 milliliters of water into the graduated beaker. Got 5, and you notice how well our volunteer did that, watching, looking across the meniscus to make sure it's 5. I guess I'd better put another insulator. What did you say the boiling point temperature was?
212 degrees.
212. Does water at 212 degrees hurt?
It sure does.
Yes, very much.
So we better be careful about this. All right. Got that? Set of glasses for you. Tiny set for me.
They're bigger than
We get this set up. Get that there. I'd like you to start up the vacuum pump while I clear away some of this clutter. All right, red lever, push it up. And you're going to be the eyes of the group because back there they can't see this too well. As soon as it starts to boil, it'll bubble a little bit and then boil and boil. I want you to yell out it's boiling, okay?
Okay.
All right.
I don't have to yell like really loud.
Well, stunning loud. Is it boiling yet? Oh, is it boiling yet?
It's boiling.
Ah, it's boiling now. So we know what the temperature is, right?
It's boiling, Jalen.
But question for the class. We know what the temperature is now.
It's boiling. Now it's being weird.
All right. This would be even better. Okay, now I'd like you to put your finger into. What do you mean? It's not a shirt.
Oh, really? Okay.
Put your finger.
No.
I've got lots of Band-Aids, so don't worry about it.
I don't want to put my finger in the water.
See the thermometer in
Yeah,
All right. There's
there. She's a science. She's a science student. Look at her.
I almost dropped it.
71.
Okay. Going down.
going down from 212.
Yeah, it's like 56, 55. It's like
What's room temperature?
71.
Do we have a problem here? Houston, what's the answer? We boiled the water, right? You said the boiling point's 212. Put the thermometer in rather quickly after taking the water out. And it's not at 210, 205, 200, 190. It's way down at 50 odd degrees. Why? Anybody even, I'm willing to wager, though I don't bet because I always lose, that most of you are not aware of what's happening. So I have to tell you what's occurring. When we are boiling the water, we are boiling it not at 212 degrees. What's the room temperature?
71.
71.
We're boiling the water at 71 degrees because we've lowered the pressure. And when you get into Charles' law about pressure, volume, and temperature, you'll find out that that is entirely correct. We don't have to have the water at 212 to boil it. We can boil it at 71 degrees. We can boil it at 55 degrees if we can evacuate to a lower pressure. And if we keep lowering the temperature, what's going to happen to this liquid water when we get to 32? Yeah, it's going to freeze. It's going to solidify. And it happens because each molecule of water that is emitted from the liquid water and goes into the gaseous state here takes a little bit of heat away from the remaining liquid. And it takes more and more and more, and the temperature falls like a rock until it gets to 32, and then it says, I'm cold enough, and snap, we're solid. If you want to do it quicker, take this up with you on your nice next space flight. And after you put on your spacesuit and helmet, walk out the door and hold this out. And like that, it's going to freeze. Because there's a big, humongous vacuum out in space. Not this teeny-weeny little vacuum pump. Lots of pumping speed. So it happens instantaneously. How about a round of applause? All right, we've covered James. I thank you kindly. Appreciate your paying attention.
Thank you.
Thank you very much.